The interstellar comet known as 3I/Atlas, officially designated C/2025 N1 Atlas, has captured global attention since its discovery on July 1, 2025, by the Atlas telescope system in Chile. As only the third confirmed interstellar object to pass through our solar system, after 1I/Oumuamua in 2017 and 2I/Borisov in 2019, its arrival instantly became a subject of scientific curiosity, public fascination, and social media-driven speculation. Unlike typical comets that originate in the Kuiper belt or Oort cloud and remain gravitationally bound to the Sun, 3I/Atlas follows a distinctly hyperbolic trajectory. This means it entered the solar system at high velocity, around 68 kilometers per second, and will depart again without forming an orbit, continuing its long journey through interstellar space. Such an extreme path is a clear signature that the object is not native to our solar system, but instead comes from somewhere else in the Milky Way, perhaps ejected from a distant star system millions of years ago. Early observations estimated its nucleus to be approximately 14 to 20 kilometers in diameter, making it significantly larger than Oumuamua and more comparable in size to a small terrestrial city, roughly the width of Manhattan in New York. Surrounding the nucleus is a noticeable reddish coma produced by dust, hydrocarbons, and complex organic compounds, such as tholins. These reddish organic materials are thought to form when ultraviolet radiation interacts with frozen ices on the surfaces of comets or icy bodies in deep space over long periods. Their presence on 3I/Atlas reinforces the idea that interstellar objects may share chemical similarities with primitive bodies from our own solar system, offering valuable clues about the broader processes that shaped various planetary systems across the galaxy. As 3I/Atlas approached the inner solar system, astronomers were excited to study a pristine object that had likely never encountered a sun-like star before. But alongside serious scientific research, the comet also became the subject of controversy. Some observers claimed that its trajectory showed unexplained deviations, that its brightness fluctuated in unusual ways, and that certain astronomical agencies were hiding information about it when it moved behind the Sun. These ideas spread quickly on social media, boosted by sensational posts and commentary from individuals speculating that the object might not be entirely natural. One figure whose comments drew attention was Dr. Avi Loeb, the well-known Harvard astrophysicist, who previously proposed that Oumuamua might have been artificial. Although Loeb's public comments about 3I/Atlas were framed as scientific curiosity rather than firm claims, they were widely interpreted as implying that the object could again be something engineered or controlled. This added fuel to online speculation, especially among communities primed to believe in astronomical cover-ups. In reality, professional astronomers studying 3I/Atlas have consistently explained that its behavior can be understood through familiar physical processes. Comets are dynamic, volatile-rich bodies. As they heat up while approaching a star, the ices within them, water, carbon monoxide, methane, carbon dioxide, and others, begin to sublimate. The resulting jets of gas and dust can push the comet slightly off its predicted path. These forces, called non-gravitational accelerations, are common in cometary motion and must be included in detailed models. Brightness changes are also normal. Cometary surfaces are uneven. Layers of ice erupt at different times, and increasing sunlight can dramatically shift visibility depending on angle, dust output, and thermal activity. In other words, the supposed anomalies in 3I/Atlas's trajectory and brightness are well within the range of normal cometary behavior, especially for a first-time visitor entering a star system. Even for local comets long studied by astronomers, such variations often require updated models and repeated observations. Another point of confusion came from reports that 3I/Atlas would be hidden during its closest approach to the Sun, also known as perihelion. In truth, nothing mysterious was occurring. On October 21, 2025, the comet reached solar conjunction, meaning it passed behind the Sun from Earth's line of sight. When any object is within roughly 10 degrees of the sun's position in the sky, the intense glare makes observation very difficult or impossible using ground-based telescopes. This is a common and predictable astronomical event and happens regularly to planets, comets, and asteroids. Because 3I/Atlas reached conjunction only a week before its perihelion on October 29, 2025, the timing was unfortunate for observers, but not unusual in any scientific sense. Space-based instruments like SOHO or the Parker Solar Probe can sometimes observe objects near the sun when Earth-based observatories cannot, but visibility still depends on instrument sensitivity, angle, and mission priorities. The idea that astronomers were deliberately hiding the comet is contradicted by the fact that all known orbital data, brightness estimates, and observation windows were publicly available through major astronomical databases. As the comet approached its perihelion distance of 1,356 astronomical units from the Sun, just a bit farther than the orbit of Mars, the excitement grew. This moment, occurring at 11:36 Universal Time Coordinated on October 29th, was described by Avi Loeb as an acid test, meaning that whatever anomalous behavior people believed they were seeing would either continue or be clarified with better data. For scientists, perihelion is always a crucial stage in observing a comet, because the increased heating can dramatically enhance activity, producing more outgassing and dust that reveal the comet's composition, structure, rotation, and fragmentation tendencies. If the nucleus is fragile, it might even partially break apart near peak heating, offering a rare glimpse into its internal composition. Many telescopes around the world prepared to monitor the object as soon as it emerged from the sun's glare and re-entered a safe observational angle. The scientific value of 3I/Atlas extends far beyond social media speculation. Interstellar objects allow researchers to test models of how planetesimals form around other stars. Every solar system begins with a disk of dust and gas in which small bodies collide, merge, and sometimes get flung out entirely through gravitational interactions. It is believed that countless trillions of such objects drift through the galaxy, but only recently have our instruments become sensitive enough to detect one passing through our neighborhood. Borisov, discovered in 2019, behaved almost exactly like ordinary comets from the Oort cloud, suggesting that planetary formation around other stars produces similar icy bodies. Oumuamua, by contrast, lacked a visible coma and showed unexpected non-gravitational acceleration, which led to debate over whether it was an exotic natural fragment or something else entirely. With 3I/Atlas, scientists now have a third data point, larger, dust-rich, and clearly active. The more such objects detected, the clearer the picture becomes of how common these interstellar wanderers are and what they can teach us about conditions in distant star systems. Despite its large size and photogenic coma, 3I/Atlas poses no threat to Earth. Its path is well outside the range of planetary encounters, and its hyperbolic trajectory ensures it will never return once it exits the inner solar system. The interest surrounding it mostly comes from what it represents, a piece of material from another star system drifting close enough for detailed study. The chemistry of its dust and gas can reveal the types of ices and organic compounds formed around its original star. Its color, surface properties, and outgassing behavior might hint at whether interstellar comets typically resemble Oort cloud objects or reflect a different formation environment. Even its rotation, shape, and fragmentation can offer clues about the stresses experienced during its ejection from its home system and the long interstellar journey afterward. As it passed perihelion and began its outward journey, astronomers expected that the comet's increased solar exposure would lead to enhanced jetting. This could temporarily brighten the coma or produce new dust features like tails, fans, or spirals, depending on the nucleus's rotation. Ground-based telescopes would soon regain visibility as the comet moved away from the sun's glare, allowing for further imaging, spectroscopic analysis, and orbit refinement. Any remaining questions about its supposed anomalies will be answered with more precise measurements. Historically, suspected anomalies in cometary motion almost always disappear once scientists incorporate detailed outgassing models or obtain higher resolution data. While it is true that interstellar objects can behave in unfamiliar ways because we have so few examples, extraordinary claims require extraordinary evidence. And so far no data has indicated anything beyond natural cometary physics. The public fascination with 3I/Atlas is understandable. Interstellar visitors stir the imagination, connecting scientific discovery with the vastness of the galaxy and the mystery of distant worlds. But the conversation surrounding such objects also reveals how easily complex scientific phenomena can be misinterpreted when stripped of context. In reality, the motion, brightness, and temporary invisibility of 3I/Atlas all fit within established comet science. Its passage through our solar system is not a sign of artificial technology or a cover-up, but an extraordinary opportunity to study something ancient, foreign, and scientifically invaluable. As it continues on its outbound journey into the darkness of space, it leaves behind not fear or suspicion, but another data point in humanity's expanding understanding of the cosmos.